Imagine a star so large that its glowing envelope could swallow the orbit of every planet in our solar system. Now imagine that the light is not powered by nuclear fusion at its center, but by a black hole quietly feeding inside it. This is the astonishing idea behind a newly reported cosmic object, the black hole star. For centuries, stars have seemed simple from a distance. They are enormous spheres of hot plasma, held together by gravity and balanced by the pressure of nuclear fusion. Hydrogen fuses into helium, helium can become heavier elements, and the released energy pushes outward against the star's own weight. Black holes appear to be the opposite. They are regions where gravity has become so intense that matter and even light can fall beyond a point of no return. Yet the new research suggests that, in a rare environment, a black hole and a star may not merely coexist. They may become one visible object. The proposed black hole star is not a black hole wearing a costume. It is a system in which a compact black hole sits inside a vast, luminous envelope of gas. From far away, that envelope could look remarkably similar to an unusual star, while its hidden engine follows the physics of accretion rather than ordinary stellar fusion. The scale is what makes the idea so dramatic. The envelope may extend across distances comparable to a solar system. Its center would be tiny by comparison, a black hole perhaps only a few times the mass of the Sun, surrounded by material spiraling inward from the surrounding gas. As that gas falls, it does not simply disappear. Gravity accelerates it to enormous speeds. Collisions, magnetic fields, and turbulence convert some of its orbital energy into heat and radiation. The result is a furnace powered by matter losing its gravitational freedom. That mechanism is familiar in quasars, X-ray binaries, and active galactic nuclei. What is unusual here is the possibility that the feeding black hole is buried inside its own thick stellar-scale atmosphere. The envelope could absorb, scatter, and reprocess the central radiation until the entire object shines with a distorted, star-like spectrum. Why would nature build such a strange object? The answer may lie in the earliest generations of stars. The first stars formed in a young universe with almost no elements heavier than hydrogen and helium. Without heavy elements, gas cooled differently, clouds could remain unusually massive, and the first stellar systems may have followed paths that no longer occur commonly today. One possibility is that a dense cluster of primordial stars collapsed toward its center. If enough mass gathered in a small region, a seed black hole could form. As it fed, radiation from the black hole might have prevented the surrounding gas from collapsing normally, creating a feedback loop. The black hole grew, the envelope swelled, and the object remained bright rather than immediately vanishing beneath its own gravity. This could solve a long-standing cosmic puzzle. Astronomers observe supermassive black holes that already weighed millions or billions of suns when the universe was still young. Standard models struggle to grow such enormous objects from ordinary stellar remnants quickly enough. A black hole star could provide an intermediate stage. Instead of beginning with a tiny stellar black hole, the universe might create a buried seed that feeds continuously inside a massive envelope. The black hole would gain mass while the surrounding structure temporarily hides how rapidly it is growing. Eventually, the envelope could become unstable. It might shed material in violent outflows, collapse inward, or be disrupted by the black hole's increasing appetite. When the envelope disappears, the remnant could emerge as a much heavier black hole, ready to become the center of a quasar or the engine of a young galaxy. But the most exciting part of this story is not only how such objects might form. It is how we could recognize one. A black hole star would need to imitate a star and betray itself at the same time. Its overall brightness might be enormous, but its temperature profile could be unusual. The outer envelope could produce a relatively cool surface while the hidden inner region generates high-energy radiation. Gas farther out might glow in specific emission lines, carrying the fingerprints of intense irradiation and fast-moving winds. Astronomers could also search for an odd combination of properties, a star-like object with extreme luminosity, a broad and shifting spectrum, powerful outflows, and signs of a compact central engine. No single clue would be decisive. The identification would depend on the pattern formed by many observations across infrared, optical, ultraviolet, and X-ray wavelengths. The reported candidate is especially intriguing because it appears to occupy a gap between familiar categories. It is too extended and too star-like to be an ordinary accretion disk around an exposed black hole. Yet its energy output and spectral behavior may be difficult to explain with fusion alone. That gap is where astronomy often becomes most productive. Nature does not have to respect the labels humans use. A cosmic object can be a star in its outer layers, an accretion system in its core, and a possible black hole nursery in its future. There is also a deeper lesson about seeing the universe. Telescopes do not photograph every object as a clear sphere. Most distant sources are points of light. Their true nature is reconstructed from brightness, color, timing, motion, and the way their radiation changes across the electromagnetic spectrum. A black hole star, if confirmed, would therefore be less like a picture and more like a forensic case. Researchers would measure its chemical composition, model the movement of its gas, compare its light with computer simulations, and test whether ordinary stars, stellar mergers, or active galactic nuclei could produce the same evidence. The word star may even be misleading. In everyday language, a star is a body powered by fusion. In this proposed object, the visible envelope could be sustained by energy released from accretion. It would look stellar, but its power plant would be fundamentally different. That distinction matters because the object would represent a new route through cosmic evolution. Stars are usually thought of as the ancestors of black holes. A massive star lives, dies, and leaves behind a compact remnant. In a black hole star, the order is partly reversed. A black hole may become the engine that shapes a star-like body around itself. Could one exist in the modern universe? Perhaps, but the conditions would be difficult. Heavy elements change how gas cools and how radiation escapes. Modern galaxies also contain magnetic fields, dust, and complex stellar populations that may disrupt the clean environment needed for a primordial black hole star. Even if no nearby example survives today, finding a fossil signature would be transformative. A distant object seen as it was billions of years ago could preserve a stage that vanished long before Earth formed. Looking deeper into space is also looking backward in time, and the early universe may be the only laboratory where these monsters were common. Future observatories could sharpen the test. Infrared telescopes may see through the surrounding gas and measure the cool outer layers. X-ray instruments could search for the hard radiation expected from a hot inner accretion region. Spectrographs could detect winds moving at thousands of kilometers per second. Time-domain astronomy may provide another clue. If the central black hole feeds unevenly, the entire envelope could flicker or brighten in patterns unlike a normal pulsating star. A changing signal, repeated across several wavelengths, could reveal that the hidden engine is not stable fusion but a turbulent flow of matter. Gravitational waves might also enter the story. If a black hole star formed inside a dense environment, encounters or mergers could disturb it. A future detector might see the compact object collide with another black hole, while telescopes observe the surrounding envelope flare in response. For now, the discovery remains a scientific invitation rather than a final verdict. Extraordinary objects require extraordinary evidence. The candidate must survive alternative explanations, independent observations, and models that account for its light without special pleading. Still, the idea changes the questions we ask. Instead of wondering only how black holes consume stars, we can ask whether black holes can create star-like environments. Instead of treating the early universe as a simpler version of today, we are reminded that it may have hosted entire classes of objects that disappeared as cosmic conditions evolved. A black hole star would be a paradox made real, darkness powering light, a tiny horizon wrapped in a solar system-sized atmosphere, and a possible bridge between the first stars and the first supermassive black holes. When you look at a star, you may be seeing a nuclear furnace. But somewhere in the distant universe, a point of light might be powered by something stranger, gravity feeding on gas, hidden beneath layers of glowing matter. The cosmos may not be organized into familiar categories. Sometimes, the most important discoveries begin when one object refuses to fit any name we already have. There is a practical reason these possibilities matter beyond their strangeness. Every proposed formation pathway leaves a different chemical and dynamical record. If a black hole grows inside a massive envelope, it may enrich the surrounding space with winds before the final collapse. Those winds could influence nearby clouds, trigger new stars, or alter the material available to a young galaxy. In that sense, the object would not be an isolated curiosity. It could act as a cosmic feedback machine. It would take in gas, convert a fraction of its energy into light and motion, and return heat and momentum to the environment. The first black holes may have helped sculpt the very galaxies that later became their homes. The search will also test the limits of simulation. Computer models must connect tiny scales near the event horizon with structures spanning astronomical distances. They must track radiation transport, magnetic fields, turbulence, and gravity at the same time. A convincing model will need to predict not just that the object can exist, but what it should look like to a telescope. That is why new observations are so valuable. A single spectrum can suggest an idea, but a time series can reveal a hidden engine. A sharper infrared image can separate a compact source from its surrounding cloud. A second telescope operating at another wavelength can turn an intriguing anomaly into a physical explanation. Whether the candidate becomes a confirmed new class or eventually receives a more ordinary explanation, the investigation is already useful. It forces astronomers to widen the map of possibilities for the early universe, and it teaches us to recognize that cosmic evolution may contain temporary phases with no close modern equivalent. The universe is not obligated to make its most important structures easy to classify. It can build an object whose outside resembles a star, whose inside resembles a quasar, and whose destiny is to become a giant black hole. That possibility is a reminder that discovery is not only about finding new things. It is about learning how many ways the old laws of physics can arrange themselves.